hz, if we put z is equal to 1, what we get is h1 would be equal to h1 as n is even. And h of minus 1 is again equal to h of minus 1. Now for type 2 filter, the criteria for type 2 filter, the criteria is h of n is again symmetric to h of n minus n, and the length is even, that is n is odd. So 0 equates to 7 and there would be no loner, and 1 equates to 6, 2 equates to 5, and 3 equates to 4. Now here in this fashion, as your type 1, if we write hz, we would come up to this. Now taking z to the power minus 7 by 2 common, we will be left with h0 z to the power 7 by 2 plus z to the power minus 7 by 2 plus h1 z to the power minus 5 by 2 plus z to the power minus 5 plus 5 by 2 to z to the power minus 5 by 2. In this fashion, if we go on, the last term would be h3 z to the power half plus z to the power minus half. And if we replace z by e to the power j omega, we are left with this. So the in general equation that we can write for type 2 is this one, that is h e to the power j omega is equal to e to the power minus j omega n by 2 into twice of summation n going from 1 to n plus 1 by 2 h of n plus 1 by 2 minus n cos of n minus half into omega. You can take n as 7 as our case is, and by changing small n from 1 to n plus 1 whole by 2, we can get different values or the previous equation for that we have derived here for type 2 we can get. This is the particular equation, whereas the in general equation for type 2 linear phase FIR filter is this. Now similarly for type 2 FIR filter, we will have hz is equal to z to the power minus n h of z to the power minus 1, where n would be odd. Now if n is odd, then we find h of 1 will be equal to h of 1, but h of minus 1 would be equal to minus of h of minus 1, that is h of minus 1 comes up to be 0. Now if h of minus 1 comes up to be 0, that means z is equal to minus 1 means omega is equal to pi. At omega is equal to pi, we have 0 value. That means we can never design a high pass filter with our type 2 filter. If we cannot design a high pass filter, we cannot even design a band pass filter. This is the limitation of type 2 filter. Now for type 3, we get antisymmetric property, that is hn is equal to minus of h of n minus n. Now if length is odd, then capital N would be even. So if capital N is 8, then again h0 would be as h8 and we have 4 as the loner. So h of z can be written in this fashion, only the difference is now h of 0 is minus of h of 8, h of 1 is minus of h of 7. So this is just the change in the equation. And if we replace it by e to the power j omega, this is instead of cos, what we get is sine. Now if it is sine, we have a phase difference of pi by 2, that is omega minus pi by 2. And so here we have 2 e to the power minus j4 omega into e to the power j pi by 2. Summation n going from 1 to 4 h of 4 minus n sine n omega. So this is the particular equation when n is equal to 4. But when n is equal to, when n in general, the in general equation would be this. where phi is equal to minus of n by 2 omega plus pi by 2 plus beta for the pseudo magnitude part, the phase for the pseudo magnitude part. Now if we take the group delay, it again comes up to be minus d phi d omega, that is plus of n by 2, which is again a constant. But here, as we see, we started with n even, but here the problem is h n of z is equal to minus of z to the power minus n h of n z to the power minus 1, and n is even. So what we have is h of n1 is equal to minus of h n1, that is h of 1 is equal to 0, and h of minus 1 is again equal to minus of h of minus 1, that is h of minus 1 is again 0. So if both are 0, both low pass and high pass filters are not possible, as well as band stop filter won't be possible. We cannot design, that means we cannot design a low pass, high pass and band stop filter using a type 3 linear phase FIR filters. Now type 4 is again an antisymmetric property, but the length is even, that is order n is odd. So here also we can write h of ej omega. This is the particular equation, and the in general equation is written here. So again the group delay is n by 2, which is a constant for a particular filter, but that is for a particular n. Now here the case is, if n is odd, n by 2 would be, say for example, if n is 7, n by 2 would be 3.5. So practically achieving such filters where the group delay is not an integer is difficult. Now here again hz is equal to minus of z to the power minus n h of z inverse, if we take z inverse of the antisymmetric property from where we started. So if n is odd, what we have is h of 1 is equal to minus of h1, that is h1 is 0. So low pass filter, and if low pass filter is not possible, band stop filter won't be possible, that is we cannot design low pass filter and band stop filter using type 4 linear phase FIR filters. So we see all the type 2, type 3 and type 4 has limitations. So the best filter among the 4 types we have studied today is the type 1 filter, which has no limitations of designing. Thank you class for now.